Hello, everybody. Thank you for taking time to join tonight. Thanks to ArchiNet for making this happen, to Mohammed and team. My name is Bhami Ilyas. I'm from CPP. I look after region for this part of the world. So today I'm going to walk you through some interesting behind the scenes in the design process that we do with architects in the community. So the title is The Beauty of Wind Effects on Architecture. So to start, we all do know that inspiration, architectural inspiration, is something very key for architects. And what we have to understand is that shape and form, of course, is something very key for architects to define projects as such. And looking back, what reminds me is the iconic German architect Frei Otto. He really changed the way how you actually design certain aspects of the architecture, and he combined that into engineering, where he was a specialist also in structural engineering, interestingly, in lightweight structures. And he used to experiment, with in terms of looking for inspiration with let's say, bubble soaps. And the superficial tension in bubble soaps or in butterfly wings. And it went ahead, looking in natural organisms in and around the environment. And we can see magnificent similar kind of work across the world that architects have inspired for their projects. And one such as what you see here at the top left is actually the Munich Olympic Stadium by Frei Otto, and quite inspired from the bubble soaps. When we try to look at architecture as such, you see we have organic and we have the geometric. And that's where things get quite interesting for us. How do we create, for these architectural projects, how do we create to make them more sustainable or safe, as what we call as safe, sustainable structures? That's where we, as wind specialists behind the scenes, come in to tie the knot between architects to work together in forming iconic structures around the world. And you would see down in my presentation how we do this, in fact, along with, of course, structural engineers as well. So it's an interesting world of science, how things actually evolve, and advances in science, how has actually helped us to be where we are today. Before we actually get into all this, we have to take a step back to understand codes and standards, because anything in this world, when it particularly comes to structures being built, there are codes, there are standards pertaining to it, and all of us know AACE, NBCC, Eurocode, and so on and so forth. In India, it's IS 875. Now, all these codal provisions that engineers and architects that refer to have its own limitations. And that is why we have to understand that codes are in general weak. They doesn't actually, in predicting for a non-typical geometry with complex surrounds and providing the correct amount of loading, that's the right refined loading that's required. So they pretty much doesn't take into account a lot of factors, in fact. Coming when you talk about structures, the inspiring structures that we see today in our day-to-day life, and I'll walk you through some of this as we go through behind the scenes of that. And then one such key thing to also bear in mind is that the directionality of a particular project in codes usually take it as a uniform, whereas in reality we go for something like the speeds actually vary from angle to angle, and that's something what you're seeing here. Now, when we look into how all this design world for wind actually has shaped it in terms of the research behind the scenes, was back in 1960s, primarily the two fathers of wind engineering, Alan Davenport and Professor Jack Cermak. Cermak is actually one of the founders of CPP back then, and he started this the company and that movement as well, in finding a lot of key research that actually that's being used in day-to-day today in our sciences. What you're seeing here in the picture is everybody would recognize that this is actually the World Trade Twin Towers back then, which was tested in Colorado State University. So you would see this, you would see the proximity there back then, how it was used by Professor Jack Cermak. And what you saw that was actually in a wind tunnel. So I'm going to show you some of that interesting aspects of how this whole process is being done. But just a bigger picture before that we get into improving the building, the building sustainability, the safety, the amenity in it. We use a different combination of tools, in fact. And so wind tunnel testing is one of it, where we have labs to test this particular process of proximity of scaled models of the cities in our labs. We also take into account the meteorology. We take into account the structural dynamics of the building, and so on and so forth. There are different elements and tools that go behind it. But something that's so key to understand is that the science behind that is something called as the Allen Davenport wind loading chain, wherein which we try to understand how a response of a structure, your architectural structure, is actually reacting to the environment. So that would be wind climate, looking at the specificity of the climate in particular place, let's say Dubai or India or Saudi or so on and so forth. We look into different cities in particular, and we have to bear in mind the influence of the terrain. How is it if it's a mountainous region? We know particularly in Saudi we have a lot of places the mountainous region. And then we'd start to look at the aerodynamic effects of the building, the surrounds, the proximity, how that is being built into, then the structural dynamic effects of the structure that comes from the structural engineer, and different other criteria that we have to take into consideration during this whole process. And this is where it gets very interesting, because we have to use the tools to give the design community the reliable loads, and what they're looking for typically would be something for the facade, something for the structure, and something for the pedestrian. There are different other components as well, so to generalize this would be very key as such. And where do we start all doing this and going for is actually to look into anemometer data particularly from airports. So excuse me. So we have anemometers across different places where actually these anemometer data are collected, and we process them for outliers, wherein which, some cases there are possibilities, these anemometers are installed to measure the wind speeds, historic, and then what happens is that these anemometers over a period of time are not really maintained. You see what I mean? And then this could be actually behind a wall in some cases, blocked by the proximity in and around it. These data become really of no use to us then. So when we, especially as we look at different parts, different cities globally, we go after them and we actually process these data. And as we enter the process of actually looking at whole of that, the atmosphere, in fact, what we call as the atmospheric boundary layer, we have to look at the profiles, what we call, what you're seeing here is, in fact, it's something being simulated inside the wind tunnel for different categories, what we call as urban, suburban, open country, flat terrain, so on and so forth. And this is something very interesting, because this has to be simulated in an environment. So simulation, you see, we are trying to simulate the real effects on the project, on your particular tower or building to on a scaled model. So, and this is how actually, if you have not seen before, this is how a boundary layer, atmospheric boundary layer wind tunnel, in fact, looks inside. And there are different kinds of wind tunnels, and you would also hear wind tunnels also. I mean, initially it started to be used very initially in aerospace industry, and that's how this came out to wind industry as well later on. So what you're seeing here, in fact, is let's take a sample here. and this would be the test project we were testing. This will be the proximity disk, and this particular disk is actually rotating every 10 degree, and so 36 directions. And there is a fan behind the scenes here that blows the wind, and then there's a spires and roughness sheets to generate the turbulence that's required for the particular site, particular location where this particular building is located. So so this is very interesting as it goes down the line. We do this all across in every cities. Like we've been working on many projects where we see Kuala Lumpur, Dubai, New York, Hong Kong, so on and so forth. Around the world, these projects are being tested, and reliable loads are being given to the design community. And fundamental, what goes behind this is actually the inside the wind tunnel we're able to do is because of the scale loss, what we call what we have studied back then, the fundamental loss, and this is actually nothing but pressure coefficients. We are able to simulate that, and it's essentially the basis of what we are testing on. One of the key aspects of understanding the wind with regard to architectural structure would be the response of this particular building in question, what we call as different responses there are, and just for highlighting what you're seeing here is we have along wind, we have crosswind, we have torsion. So these are some key responses of the building, and interestingly, what we do is that we find out that some of the buildings, when we get into, we really have to work on the exterior, the architecture of it, and we have to actually come up with solutions to try to dampen the wind. And how can we do that is different process of playing with the foam, the exterior of the foam, and then this is where we and architects actually go to the drawing board to see where we can actually cut down the loads that's actually governing the design, the wind loads. So one such approach is actually to look at softening the corners of your building, or you can actually go tapering the building. In some cases, you can go and in varying cross section, that will also helps. Adding in sometimes spoilers and porosity and openings, as well as twisting in some cases. So this is what you're seeing here is some quick examples of how this actually looks like, and we tend to actually iterate this particular process. So this becomes a very good exercise for the once you have a project in mind that you really need to reduce the loads which has been governing. How can you bring these design loads down so you can save money? This is first thing on the table, actually, to go back and look at the design, how it's been interacting with the wind, and then work out a solution to it. Now I'm going to show you a quick, small, few second video in which you'll see a typical structure. This has no sound. And this is sitting in it's a cylinder that's sitting in the tunnel, and you can see it's moving. Now, if you closely observe that, actually, what you see here is, in fact, it's moving, and look at the red dot, you can see. Now, this is, if you recall my earlier slide, I did mention about crosswind loading, and this is where it gets very interesting. This particular structure is actually moving to the crosswinds in there. So what I'm going to do, I'm going to show you something else to that to understand that. Now, as a man, we are not able to actually, humans are not able to visualize that, right? So let me show you something that you're able to visualize on how this actually looks like with a water dye. So this is actually the shedding of vortices, what we call, and water shedding being explained beautifully here in this particular video. And this is what you're not able to see with your naked eye, and that's what we are actually trying to solve here. So this particular effect actually changes buildings to buildings, and with the neighboring building it changes. Then there is difference of the behavior changes totally. Now. We did something tweaked to that, a very, very simplified approach of adding a streak to it, a helical streak. Let's see what happens then if you observe on this particular short video. This has no sound. And if you, now the camera would just zoom in, and you can see the response of this particular cylinder has been dampened. When I mean dampened, it means controlled. Prior to the previous one, the movement has been reduced much. And this is all because we added in the helical streaks. And now if you just recall, this particular cylinder and helical structure, you would have noticed somewhere else. And this is in industrial chimneys. This particular design is very prevalent. And that is the reason why you see this in industrial structures. They have helical streaks to actually reduce the shedding. Now I have an example of how of the response of the wind in a lightweight setting. Let's see, lightweight structure setting. I believe we have sound on this, so I'm going to reduce it, maybe too loud. Let's see. And another example of a chimney without a helical streak moving. So it's interesting to see. We have to do different and when different approaches to actually to control and confuse the wind. So that's one of the key things we have to be doing. And just doing a very closer look at how this architecture is behaving to the wind. Another way of looking at it is graphics, where we use something called as a CWE analysis, computational wind engineering. So most of you would be aware with CFD, computational fluid dynamics, and CW is a branch. CWE is a branch of CFD, in which wind engineering applications are being studied. So this is a quick view of how the flow works. This has no sound. In and across different dimensions of 3 blocks. And you can see how different these particular things vary. The idea is to show you how the vortices have been shed. You change one particular parameter and the dynamics of the building reacting is completely changing. And now you're adding to that your surrounding neighbors, the mountains, the terrains, the topography, everything changes totally, place to place. And that's where, things get very interesting in terms of the design. Now, one of the other key things we could do, apart from what I've shown earlier, is also similar to actually going back, and this is a good example to that, is, in some cases, MEP pros, we try to do different configurations, closing and opening and chamfering, and then, in some cases, adding in spoilers and so on and so forth. So, and to see how this actually varies with regard to the responses that we are seeing. And one of the questions now we have to remember is that in buildings, there's a separate topic actually. It's called damping. And interestingly, what you have to remember that when you're talking about really high-rise towers, there's something called as accelerations. So accelerations, let's assume you are in a very high-rise tower at the top, you have a penthouse, you're living in there. If the building has a very high acceleration, you're a tenant to that place or you own that place, what you would observe if it has high acceleration, you would feel the building is actually moving. It's a perceptibility, it would vary person to person. There's still a lot of research ongoing on that. We could talk for hours actually with regard to accelerations and damping in buildings. Now, the interesting key point in here is that we as engineers and specialists, we tend to actually dampen that always. We have to be mindful of that. And particularly once the architects and the structural engineers come to us, once our results are published, to them, this is something, one of the findings that we look for, and then we try to see how we can actually dampen it. In some and most of the cases, we can actually adjust the structural dynamics of how the structure itself is behaving, and probably try to make corrections. Or we also go and explore the option with the architect to see how can we change the architecture minimally. And that is where it gets quite interesting, because as architects, it's not always we have a floor space to actually go and change. So that's where it's sometimes very challenging. Now, so with really high accelerations, if it's an office space, there are different criteria where it's acceptable compared to a residential space, and that is where in really slunter buildings, particularly you would see in downtown areas of various cities where there is a possibility damping systems have to be involved. And then there are different kind of dampers that would go, whether it could be a simple TMD or FVD, fluid viscous damper, so on and so forth, that have to be employed in order to actually control the wind resistance. And this is a quick slide to show you how actually all that changes, in fact, is actually helping, because if you see the squares cross section, it really gives a very good crosswind response high, which we really don't want. We want something, the red line, which is a lower response compared to, so you can see a circular, a hexagonal, and partly tapered has given us a lower response compared to the other shapes. Now, how does this whole process take place? It's something behind the scenes. Is what you look here is, in fact, this is our labs across the world that we have. Primarily the main office in the US and in Australia, where we have model shops actually to build these particular project models. Many of you would recognize this particular building in Dubai. It's a very iconic building coming up in Dubai. Please. So let's take a look at the flow separation actually. So what you're seeing here is a flow visualization test, and this is something to understand, to show you. It's difficult to decipher sometimes because we see this every time, so we're able to decipher it quick. But to the naked eye, it sometimes becomes challenging. But the idea here is that to show you how this the flow dynamics is actually changing around the particular corners. So to the top right here, pressures measured on a wind angle coming in this direction, the green versus the yellow here, you can see that at the corners here is actually more suction, and that's why there's a larger curve, CP values going higher in magnitude actually compared to the positives in there. So this is exactly what we are measuring in the wind tunnel, every space of the building in general. So ideally, you would see in a very second why we ideally cannot actually go in every DX point of the building as such, because of the technical limitations of having them instrumented into the building. But you would see our aerodynamists actually go in and pick the key locations actually to instrument the sensors in the building to understand how these particular buildings move on, respond to the wind. Yeah. So this is a shell view of how the models look like, and these are typically in the range of 1:300 to 1:500 from a full scale. Scaled down versions, what you're looking at here, and these are actually the sensors being drilled onto the building. This is another example of the same. What you're looking at here is one of the key projects we have done some time back at the Marina Bay Sands. You can see there's a spaghetti of sensors actually, in fact, the wiring system below the wind tunnel, what you're looking at here in this particular picture. This is another process of different viewpoints of how a particular building looks in different stages. Now, I'll show you how these different stages in fact look like. So typically we get from the architect the Revit model, and we kind of process it with sensors where it's actually required aerodynamically, and in our format required. We actually 3D print them, or something called a stereolithography machine that we use, and then we bring them actually, once we have hosted them, we have tested them in the wind tunnel, we then bring them actually with the data. Now what we have to bear in mind is that there is something else also happening at this particular circumstance. We are taking all this information, we are testing, we are getting the CPs out of it, the data out of it, and at the same time then we have to add in the wind climate data. How is the particular location, a particular city, how is the wind behaving in that, historical records of that particular place that we get from airports around the world. And then we have to add in the structural dynamic properties of the building. the structural engineer, which usually is your mass, your MMI, your different mode shapes, and so on and so forth. All this has to be analyzed. So we do that in a post-processing, and then we come up with the results for the design. And one of the ways how this looks is also in terms of for facade pressures is what you're looking at here in terms of PSF. This is shown in PSF, and you can see here we can identify, particularly in a particular building on an elevation, how these loads are actually varied. You can see in some places it's 100, some places it's 50, so on and so forth. So the cut and wall consultant looking at this actually is going to do a lot of in fact, they're going to process this further from once we hand it over to actually look at what kind of cladding need to go in. And so the way to do in terms of the results, we have different approaches, and every client and every design team that we work with have different recommendations and approaches to it, and based on that we actually tune them. This is another beautiful project that we worked recently in the region. Before we move on to some of the key items, I would like to show you a case study, an example, in fact, how things actually didn't really go well when you really don't consider wind in terms from a pedestrian comfort, a pattern comfort of view. We were looking earlier on cladding facades, we were looking at the structural loads, but this is something with regard to the comfort of the pattern comfort, the people in and around using your particular space, let's say hotel, let's say residential area, so on and so forth. And we know failures do occur all the time. And when once we do not actually account for these in our design, we do know that. So one of the key things to bear in mind is that, particularly from a pattern comfort perspective, in a high rises, you can see that a tall building, the wind can actually concentrate at its base, and once you have an openings to a building at the base may induce really high pressure or funneling effects, what we call, in those openings. And one very good example is the Bridgewater Place in UK. This is some clips from BBC and other news sources. What happened? There was a person actually was killed, unfortunately, because a lorry got toppled out. A gust of wind around this particular building, and a bypasser was actually killed, and they had to shell out a large amount of fee to the council actually to actually go back and mitigate this particular place and to find a solution to it. So we were actually later on involved. We were called in to help find a solution, part of the team, design team, to find a solution. And part of that was, this particular place really didn't have any kind of instrumentation to actually confuse the wind, I would put it that way. So we had to come up with wing-like special structures. What you see here, there's yellow coils in here. These had to be installed in and around the building to actually prevent, to give a safe passage for the people actually going by. So you can see how things get complicated in some parts of the world, when it's really windy. And even here, there are places near downtown as well as in other parts of the city where actually it gets really windy. And this is the example of what was installed, as you see here. And we do this all the time in different cases. It could be sometimes in a high-profile restaurant you're working on, in which you could see really high wind flows coming in, in which the people really having you're there to have a business lunch or a casual dinner. Your napkins are flying off, and you cannot probably sit there for a long time. So all this is analyzed, and there are different categories to actually analyze this kind of pattern comfort in and around your building space. And this is very important because as we go into, particularly for hospitality sector, this becomes very important for making sure the guests are very well comfortable in and around the environment. So we do this for cities, and we do this for particular projects. We come up with different laws and criteria to look at how the wind is interacting in and around the environment, just in terms of looking at the pedestrian, the pattern comfort. Excuse me. So we would have to go down to classify them something as the pattern sitting, standing, walking, business walking, and then there is something called a flag. It becomes very uncomfortable in some cases. So particularly at the top levels of the building, in some penthouses or the restaurants at the top of the building, that there are cases, and even at the bottom of the buildings, so on and so forth. So we identify this, and then we work with the design team to actually go in and mitigate what's the best solution to it. Now, which is the right tool to use? I would say this depends again, and depends on what you're looking for. So your facade, your structure as such would be something analog, which is a wind tunnel is the best reliable that can be offered. But where you're looking at a pattern comfort, you can bring in a computation approach in which you can perform this in something. What you saw earlier was a CWE assessment, computational wind engineering assessment, to understand this. This is very important to actually look at it, because the right tool is very important in the design process, and to give you the reliable also, that becomes key. Some of the beautiful iconic projects that we have worked in the region, many of you would identify this particular buildings in there. Very interesting buildings that we have happened to work in the recent years. With this, thank you for your time. I have an example, in fact, a snapshot of a bridge here, Choluteca's bridge in Honduras, and this is in fact this particular bridge is an example of back then there was a hurricane called Mish that went across, and you know, this is a resemblance to look at it. You know, these are challenging times for everyone around the world. Particularly in this is a very relating experience, because this particular bridge was built. I mean, it was commissioned later on. What happened was the roads that was connecting both sides had got damaged. The river that was flowing underneath the bridge actually changed the path to the right. So what we always build to last, but then changing scenarios, we should build to adapt. And I think everything we have to look down into the future. With that, I conclude. And any questions?
Thank you, Bhami. We notified everyone if they have questions to share it now. Okay, we have a question from Hamza. What is the best website to find the exact direction of the wind, like in Saudi Arabia?
So the best direction, if I heard you the question right, the best direction to find the wind. So there are different approaches you can actually take to going in to look at from a coordinates perspective, to look at, you know, which direction is the wind coming from. You can just email me. I can send you a list of them, in fact. But the key thing is to understand, and this is my email, as you can see here. The key thing is to understand that the direction, of course, is quite key, and how that particular terrain is going to be accounted in your analysis. And if you're taking a caudal approach, and you have to be very careful that you're not under designing or over designing the structure. So, yeah.
Let me give you the question a different way. Is there any websites that we can find online or some application that can give us the direction of the wind wherever the project is?
That's correct. There are a couple of websites in general. Top of my head, I couldn't remember, but
no worries. Okay, but you can share it later on with us.
Definitely. Please,
okay.
Yeah.
Okay, so this question from from Abdullah. What factors determine the wind pressure?
So it's a very fundamental and interesting question, because we could actually go on and on actually in terms of understanding what the factor would be in determining the pressure acting on the structure, and it would start at the structure, of course, how the architecture of the structure is. It will start then. We have to look at what particular city this particular structure is located in, the climate part of it. We have to look at the complex proximity. What kind of a proximity are we looking at this particular structure? So this particular structure is located. So this three would be the key. But then again, if you recall my my slides earlier, wherein which talks about the Allen Davenport chain. In fact, all that different aspects has to be taken into account to really come down to a particular pressure as such. And then too, I should add that, you know, caudal provisions are very, and that is why are very limited in general. And that is why we do not recommend them. And around the world, it's not recommended for non-typical structures.
Okay, another question. Does material really affect or change consideration and wind effects in the buildings?
The short answer to that is no. And why? Because when we are modeling in the wind tunnel, what happens is that typically, what we're using is a resin. It's a form of a plastic. That's actually what we're 3D printing with. And why it doesn't really, it really doesn't matter, because we grow them out of the stereolithography machine, instrument, tap them, measure them, and that is being post-processed with a lot of other information, and that is being applied to the structure as such. So the material of the structure in there is not in question when it comes from the design side.
Okay, this is another question from Kaiba. How important to consider aeroelastic and aerodynamic damping in wind response assessment?
It is a very interesting question, and because the aerodynamic damping need to be considered, particularly when we're this damping side of things particularly get complex when you're talking about high-rise structures, and that's essentially where we're talking when let's take a step back to see the basic. One of the basic is that a thumb rule is that you are somewhere in between around 30-story, 25 to 30-story. It is sitting on the fence. Your particular building is sitting on the fence of it, if you can go in a caudal provision versus a wind tunnel. And as the building gets taller, the wind actually is governing your design, and then you have to take into account different damping criteria that have to come into play. And it's a function of how your architecture is and how your dynamic properties from the structural engineer that's coming out. And then we have to make an assessment based on that.
Okay, another question from Hatem. In design, do you consider the climate change, which will have a role in changing the wind conditions, design wind speed and turbulence levels?
So if I understood that right, Mohammed, so you said could you repeat that for me? If you said that
okay,
the climate.
Let me repeat it. In design, do you consider the climate change, which will have a role in changing the wind conditions, such as design wind speed and turbulence levels?
Very, very interesting question, and it's a debatable one, and it's of current interest, in fact, because the climate change, as you see around the world, is happening. But one of the key things when we actually work on is we are looking at historical data. So we are designing a particular project at this point. We're looking at 50 to 100 years back. In terms of a couple of decades, to see how the responses has been, particularly, let's say, hurricane regions, typhoon regions, how these buildings were behaving, and we look for the peak loads in there, and that's how we actually design. So yes, in a sense, we do take into account the climate, but there is a lot of research that's ongoing how we can actually take into account what's not coming, what's may come in the future as such.
Mm-hmm. Okay, another question from Abdullah. There are positive and negative wind pressure. Which one usually is bigger and why?
Again, Abdullah, very, very nice question. So typically you would find it's difficult to just say any one is actually dominating, but negative pressures, the suction, what we call, is actually, we could tend to find, in a given facade or an elevation of a particular project, maybe on the higher end. But nevertheless, we also have seen positive pressures also going up really high. But in general, to say it would be negative pressures that I have seen that goes really high, suctions, I would say. Yeah.
Okay, so we finished all the questions. Thank you a lot. I don't know if anyone have a question. You can send it within less than 30 seconds. Sorry.
And always, yeah. And always, please do take down my email as well, and more than happy to. You can reach out to me for any.
Bhami.Ilyas@ccp1.com, right?
cppwin.com. That's correct.
You only based in Emirates. Do you have any representative in Saudi or something?
Not at the moment, but as you know, with Saudi, yes, we are closely associated with Saudi as well.
Yeah, it's very close. Yeah, we plenty of UAE companies already here. So
yes.
I think we are done. Thank you a lot for this comprehensive presentation, and thank you for everyone for their attendance and the nice questions that we had. Thank you.
Thank you, everybody, and thank you, Connect Mohammed, for having me. Thanks, everyone, for joining. Good day.
See you soon. Thank you. Take care.